Algebra 2, we are in Chapter 4, Section 6. All right, let's warm up and remember what we've learned in the past. Okay, I just rewrote it down here. If you remember our log to exponential form, it's necessary to remember, right? Right, so let's put this in exponential form. So there's my base. So we have, and this is my y, and here's my x. So we have 3 to the 4th equals 2x minus 7. Okay, now in this lesson, we are going to learn how to solve this, which isn't too bad. Okay, now let's put this in log form. Log form, if you remember early on in our lessons, helped us solve for a variable that is in the exponential spot. So here I have log base 8 of 30 equals x. And again, we are going to be able to solve this starting today. All right. Solve the equation. Yikes. If I have b to the x equals y and log base b of y equals x. So we're going to have log base 100 of 1000 equals x. Now this right here, I can simplify this because it is the same as, we're going to change the base, okay? Log 1000 over log 100 equals x. Right there, in my handy dandy calculator, that's equal to 1.5. Okay, again here, I'm going to change this into exponential form. So I have 5 to the negative third equals x. If I take 5 and raise it to the negative third, I get 0.008 equals x. Even if you kept it in fraction form, that'd be 1 over 125, which was the same as 1 over 5 cubed, because that's a negative exponent. Okay, solve the equation. Ooh, let's remember this. A times c is negative 60. So two numbers that split up, multiply to negative 60 and add to negative 7. 5 times 12. 5 times 12, where the 12 is negative, gives me 60, and if I add those, I get negative 7. So x plus 5, x minus 12 equals 0. If I solve, okay, I'm reminding you here, x equals negative 5, x equals 12. All right, moving into our lesson. Exponential equations are equations in which variable expressions occur as exponents. The result below is useful for solving certain exponential equations. So the property of equality for exponential equations, if b, your base, is a positive number other than 1, then b to the x equals b to the y if and only if x equals y. Okay, we're going to use that. Example, if 3 to the x equals 3 to the 5th, then we can just say that x equals 5. If x equals 5, we can go backwards. Then I can say that 3 to the x equals 3 to the 5th. Okay, we're going to use both this property. Okay, let's try one. Okay, I have 4 to the x equals 1/2 to the x minus 3. Let's get those both into 4. So this actually, I already skipped a step. First, I'm going to say that this is the same as 2 to the negative 1, x minus 3. Okay, can I change this into a base of 2? Because 2 squared is the same as 4. And I'm going to take this out there and multiply it. So that'd be a negative x plus 3. I just did negative 1 times x, negative 1 times negative 3. Now that rule holds true. I have a base of 2, therefore the exponent spots are equal to each other. So I can just go straight to 2x equals negative x plus 3. That gives me 3x equals 3, x equals 1. Again here, let's see, I have a base of 9 and a base of 27. A common base for both of those would be 3 squared and 3 cubed. Right, simplify. 3 to the 4x, 3 to the 3x minus 3. Now when I have the same base, I can take those exponents and just set those equal to each other and solve. So x equals -3, which is true. Okay, try another one. Okay, I have base of 100 and base of 1000. I can change both of those into a base of 10. That's a 7. Doesn't look like a 7, does it? Okay, this would be 10 to the third power. When there's 3 zeros, it's a third power. 2 zeros, second power. 3x minus 2. If I distribute those, I have 10 to the 14x plus 7. 10 to the 3 times 3 is 9x minus 6. Same base. I can take the exponents and set them equal. 14x plus 2, 9x minus 6. Okay, 14 minus 9 is 5. -6 minus 2 is -8. Ooh, x equals -8 over 5. That doesn't feel good, but it's correct. And another one. 3 1/3. Let's move that into the ground level position by saying 3 to the -1. Now, 81. 81 is 3 to the 4th power. Yep. So that's the same as 3 to the 4th power. And, oops, forgot that. I'm going to distribute that -1. 3 to the -5x plus 6. These are the same base, so I can go straight here. I'm going to distribute that 4. 12 minus 4x equals -5x plus 6. Let's move the 5 to the left. Keep it positive. I get x. And -6. Sweet. All right, next example. Here I have this in that the x in the exponential position, and there is nothing common about a 4 and an 11. So that's not going to work, is it? But I can take the log of both sides in algebra. If we do something to the left side of the equal sign, we can do it to the right side of the equal sign, and the world is still in balance, right? I know you guys laugh at me when I say that, but it's okay. If I take the log of the left and the log of the right, then life is grand. Now this rule, where my exponential spot drops in front, holds true. And then I divide both sides by log 4, just like math. Okay, algebra, I've now got x by itself. And I need my calculator. Log 11 divide by log 4. 1.73 approximately. Moving on. This right here is just, I need to introduce the equation of Newton's law of cooling. We just collided with science because I love science. An important application of exponential equations is Newton's law of cooling. This law states that for a cooling substance with initial temperature T sub 0, the temperature T after T minutes can be modeled by what's given, where T sub R is the surrounding temperature and R is the substance's cooling rate. Okay, here's our example. We're going to work with that equation. You're driving on a hot day when your car overheats and stops running. It overheats at 280 degrees Fahrenheit. and can be driven again at 230 degrees Fahrenheit. If my R value is 0.0048 and it is 80 degrees outside, how long in minutes do you have to wait until you continue driving? Okay, stop fretting. This isn't that bad. Okay, let's grab our equation and plug in our knowns. Here is our equation. What do we know? I know that my original, or my t, is 230 degrees, because that's when I can start driving again. My t sub 0 is 280 degrees. That was my initial. Outside, it is 80 degrees. We have R is 0048, and I think that's it. Let's plug it in. So 230 equals 280 minus 80, e to the negative 0048 t plus 80. Okay, we know this is an exponential problem because there is a variable in the exponent right there. So I'm going to work on trying to simplify this first. Okay, cancel that out, and I get 150 over here. 280 minus 80, I can go and simplify that to 200. Now we just have our exponent on the right and just a constant on the left, our variables on the right too. We can take the natural log of each side. When we have an e present, we take the natural log. 150 is, actually, hold on. I'm going to simplify that just a little bit more. If I divide both sides by 200, I actually simplify it better. Okay, so I get 0.75 here. This will just save a step. Now I'm going to take the natural log of both sides, because the natural log of e raised to something. Actually, this right here simplifies to just 0.0048t. And if I take the log of that, okay, divide by both sides, I'm left with t equals about 60. Okay, so that was a scary problem, but everything worked out just fine, right? I should say that 60 means you have to wait about 60 minutes until you can continue driving. All right, let's practice some. So solve this equation. I've written these back up here because these are what we need to remember to solve, and we can do it. So here I have log base 2 of 5 equals x. So I can do change of base. Log base 5 over log base 2 equals x. Type it all in, and I get x is about 2.32. Okay, same format. I'm going to do log base 7 of 15 equals 9x. Change of base. Log of 15 over log of 7 equals 9x. Okay, let me grab a calculator. So log 15 divided by log 7 is about 1.39. That equals 9x. Now we divide both sides by 9, and we get x is approximately 0.155. Okay, I can't change the base on this one until I move that 7 over. I have to isolate the part with the exponent. So this gives me 4e to the negative 0.3x equals 20. Now I'm actually going to divide both sides by 4 also. E to the negative 0.3x equals 5. Now I can do now I can put it into a logarithmic form. We're doing natural logs, so the log base e of 5 equals negative 0.3x. Log 5 is 1.61 approximately. Now I divide both sides by 0.3, negative 0.3. and I get x is approximately 1.61 divided by 0.3. Make that a negative. I'm not using my normal calculator, so I'm struggling here. There we go. X is approximately negative 5.36. All right, moving on. Solving logarithmic equations. Logarithmic equations are equations that involve logarithms of variable expressions. You can use the following property to solve some types of logarithmic equations. So here we have algebra. If b, x, and y are positive numbers where b can't be 1, then log base b of x equals log base b of y, if and only if x equals y. Okay, so an example. I've got log base 2 of x, log base 2 of 7, so we can say x equals 7. Or, if x equals 7, I can say log base 2 of x equals log base 2 of 7. Okay, those are crazy examples. A little weird, right? But, I can't spell, there we go. But let's do an example and it'll all make sense. Okay, so here, whoa, that's really crazy. But I see that I've got log base 5 and log base 5. Therefore, I can say that 4x minus 7 equals x plus 5. Okay, they sort of, it's not really cancel out, but that's the algebra behind it. The property of equality for log equations is what we're using here. Now we're just going with some straight old algebra, which makes my mind very happy because I'm a math teacher and a little bit strange. So 3x equals 12. X equals 4. Okay, glorious algebra. And that was the only example of that one. We'll practice some more in a second. Okay, exponentiating, that's a dollar word, to solve equations. The property of equality for exponential equations implies that if you are given an equation x equals y, then you can exponentiate each side to obtain an equation of the form b to the x, b to the y. This technique is useful for solving some logarithmic equations. Let's try one. Okay, log to the base 4 of 5x minus 1 equals 3. Okay, a little bit strange, but if I take 4 raised to the log base 4 of 5x minus 1, which looks super crazy. But if you remember, in the last lesson we learned that when these match, I can say 5x minus 1 equals 4 to the third power is 64. Okay, this side of the equation simplifies quite easily and gloriously. Now, we just get some algebra. 65. 5x equals 65. Divide both sides by 5. And I get x equals 13. Okay, that's your trick right there though, right? And another new thing. Extraneous solutions. Because the domain of a logarithmic function generally does not include all real numbers. Remember, the domain is limited. The range is all real numbers, but the domain is not. Be sure to check for extraneous solutions of logarithmic equations. You can do this algebraically or graphically, okay? We just want to check things. Check means plug it back in. So, what are the solutions of log 2x plus log x minus 5 equals 2. Okay, I have a plus, and they're both log base 10, which means I can say log of 2x times x minus 5. Remember the rule we learned in the last lesson, that addition between logs is multiplication. Okay, this gives me log base 10 of 2x squared minus 10x equals 2. Okay, now I can say 10 to the log base 10 of 2x squared minus 10x equals 10 squared. Now we just said when these match, this comes down. So I get 2x squared minus 10x equals 10 squared, which is 100. Okay, now I'm going to use a new page and move on. And this is what I'm going to write down. So 2x squared, I think it was minus 10x, equals 100 is where we are. Bring 100 to the left by subtracting it from both sides. Now I'm going to divide everything by 2. So that gives me x squared minus 5x minus 50 equals 0. Okay, factor it. X minus 10, x plus 5 equals 0. Therefore, x equals 10 or x equals negative 5. Okay, these are my two possible solutions, but I need to check them. So x equals 10 or x equals negative 5. Okay, I'm going to substitute them in for the original equation. So we have log of 2x plus log of 10x minus 5 equals 2. This is log of 20 plus log of 5 equals 2. 20 times 5 is 100 equals 2. Remember, that's base 10, so 10 squared equals 100. That works out. Okay, let's check the other one. I have log of 2 times 5 plus log of 5 minus 5. Hold on, it was negative 5. Sorry. Equals 2. So this gives me log of negative 10 plus log of negative 10 equals 2. Can't do this. I can't take the log of negative numbers. So x equals negative 5 is not a solution. Okay, we discount that one. It's called extraneous. Okay, we could also graph it to double check. Okay, so here's my original equation. And then I can graph y equals 2 in the same coordinate plane. The graphs intersect only once, which is when x equals 10. So 10 is the only solution. Cool? All right, let's try a practice. Solve the equation and check for extraneous solutions. Well, for this one I can say, since this is base e, I can say e to the log base e of 7x minus 4 equals e to the log base e, which I don't have to write that, 2x plus 11. So since these match, I can bring that down. We can say 7x minus 4 equals 2x plus 11. So minus 2x is 5x, plus 4 is 15. Divide both sides by 5, and I get x equals 3. Another one, log base 2 of x minus 6 equals 5. I'm going to put this into exponential form. 2 to the 5th power equals x minus 6. What is 2 to the 5th power? 2 raised to the 5th power is 32. X minus 6 plus 6, I get 38. Cool. Okay, another, solve the equation, check for extraneous solutions. Okay, remember I've got the same base of 10 and plus in between, so I can multiply the 5x and the x minus 1. Then I can say that 10 squared equals 5x squared minus 5. Get everything to the same side of the equal sign. 5x squared, oh, this is minus 5x. Almost made a mistake there. Subtract 100 from both sides. I can divide everything by 5, which gets my math a little bit easier. x squared minus x minus 20. Okay, this factors into x minus 5, x plus 4. Therefore, x equals 5 and x equals negative 4. One of these is extraneous, so we need to check it. Okay, next slide. I'm going to check this into, I had x equals 4 and x equals negative 5. So plug them both in. Oh, yeah, log, I think, oh, hold on. Sorry, it was positive 5 and negative 4. So let's go ahead and plug it in. Log of 5x plus log of x minus 1 equals 2. Well, this right here gives me negative 20 and, gosh, negative 5. I can't take the log of a negative number, so that one doesn't work. So I'm pretty sure 5 works, but let's go ahead and check it. Log of 5 times 5 plus log of 5 minus 1 equals 2. So log of 25 plus log of 4 equals 2. 25 times 4 is 100 equals 2. So 10 squared equals 100, which is correct. Therefore, that is the right answer. Okay, one more. Solve the equation. Same type problem. I've got addition in between the same bases. So we'll do log base 4 of x times x plus 12 equals 3. So 4 to the third power equals x squared plus 12x. Solve or set it equal to 0. X squared plus 12x minus 4 to the third power, which I should have memorized, 64. Now I need to factor it. 0 equals x, negative 64, multiplies to 64, adds to 12. 8 times 8, no. Let's see, 64 divided by 12, nope. 64 divided by 4. 16 and 4. So if I make that a negative, that would give me negative 64 and positive 12. Cool. So x plus 16, x minus 4. So x equals negative 16, x equals positive 4. I need to check both of these. Negative 16, positive 4. So let's plug them in. Log base 4, negative 16 plus 12. I see that gives me negative, so I know I'm done. Because I can't take the log of a negative number, so that doesn't work. Log base 4 of 4 plus 12. And log base 4 of 4. 4 plus 16 is 20. Times 4 is 80. So I have log base 4 of 20 times 4 equals 3. 4 to the third power equals 80. That doesn't work. Does it? 4 raised to the third power, 64. I've made a mistake somewhere. Oh, right here. Okay, it's 4 plus 12. 4 plus 12 is 16. 16 times 4 is 64. Whew, that was a close one. All right, your favorite word problems. An apparent magnitude of a star is a measure of the brightness of the star as it appears to observers on Earth. The apparent magnitude m of the dimmest star that can be seen with a telescope is given by this function, where d is the diameter in millimeters of the telescope's objective lens. If a telescope can reveal stars with a magnitude of 12, what is the diameter of the objective lens? We see D is the diameter of the objective lens, and that's what we're trying to solve for right there. Magnitude 12 is what we have right there. Okay, so we're trying to solve for that. So let's go ahead and try it. I've got m equals 5 log d plus 2, where m is 12 and we're solving for d. So I have 12 equals 5 log d plus 2. That's a beautiful 2. So I'm going to subtract 2 from both sides. And I'm going to divide both sides by 5. I need to isolate that variable. Okay, so 2 equals log base 10 of d. So 10 squared equals d. D equals exactly 100. So the diameter is 100 millimeters. What if, example 7, magnitude was 7? So that means we would have 7 equals 5 log d plus 2. Subtract 2 from both sides. Divide both sides by 5. So, it's log base 10 of d. So 10 to the first power equals d. Therefore, d equals 10 millimeters. Okay. Oh, daily homework quiz. I'm going to say I left the answers on here, but these are the extras, okay? So go ahead and practice them. I'd be happy to help you if you don't just skip through these, right? Second to last slide. Okay, we got this. Nice work, Algebra 2. Okay, super duper proud of you. Gold or pen star. See you later.